Previously on the head of a pen.
The quarks in the second family are called the strange and the charm quark. Then there's a third family, the bottom and the top quark.
We think of quarks and electrons and so forth as tiny little points, but that description of nature has a problem, and there are infinities. If you say that the electron has no size, does that mean all of its charge is concentrated at a single mathematical point? If so, if you try to do the calculation of the electron self-energy, it explodes. You can't, you get an infinity. It tells you that there's an infinite amount of energy required to put all that charge in one point. So we all know in our minds that it must be that the charge is spread out in some way in space.
So to start with, everything is a model, and then experiment comes and tests it, and most models prove not to correspond to reality, and a few, usually one, corresponds to reality, and it becomes the standard model of that time. And that changes with time. And so there is physics and there is mathematics. Mathematics is the world of all consistent mathematical structures, and physics is, there is only one of these mathematical models that correspond to the physical world. And physics needs experiment to confirm a given theory. So when we propose several different theories, hopefully they can all be tested. Now, string theory can also be tested. For example, that the LHC, if these theories with large dimensions that I was telling you about are correct, then LHC will test these theories, and if it confirms them, they will be confirmation, they can lead to confirmation of string theory, direct. Production of strings at the LHC is a theoretical possibility. Whether it's realized or not, only experiment can tell.
The other interesting thing about the string hypothesis is that these one-dimensional entities, like an electron has some piece of string, some one-dimensional entity that corresponds to it, they travel in something like 10 dimensions. Or 11 dimensions if you want to include a dimension of time. Instead of traveling in the 3 + 1 dimensions of space-time that we're familiar with, these objects travel in and vibrate in 10 + 1 dimensions of space-time. Yeah. All right? And we don't see the other 6 or 7 dimensions because they are curled up or compactified so tightly that they do not become evident in our normal everyday life.
So imagine we have a one-dimensional universe. That is, everything we know propagates along this one dimension. Now imagine there's a knot in it. Can that knot propagate? I asked a string theorist this question once. I mean, and can you imagine complex sorts of knots which, if those two knots collide, they make a different knot? Well, in higher dimensional spaces you can do stuff like that. You can have topological defects which have sort of integer classifications. In other words, you might say a simple knot is a number 1 knot. A double knot is a number 2 knot. But you can't have a 1.5 knot, right? A knot is a knot. It's either the next level of complexity or not. So we see that particles have integer quantum numbers. Where do these integer quantum numbers come from? Space and topology, topological defects could, certainly, geometric objects in higher dimensions are described by integer type things. So we need something that gives us the mass of particles, their interaction strengths, their intrinsic angular momentum, their spin. This is a tall order for whatever theory you're going to come up with, but It certainly appears that the way theorists are thinking, it's along the lines of higher dimensional spaces and the mathematics that obtains there.